Hello, this is Lei Wang from Institute of Physics, Chinese Academy of Sciences in Beijing. Thanks the organizers for inviting me and for putting together such a wonderful program. I enjoyed very much all those talks. So I'd like to talk to you about tropical tensor networks for the ground state of spin glasses. This is a collaboration with my former postdoc Jingguo Liu, who is now moving to Boston, and a friend of mine, Pan Zhang, who works in ITP, that's the Institute for Theoretical Physics, also belongs to Chinese Academy of Sciences. So those two, they are actually the main players behind this project. I'm mostly being a cheerleader for them. So by the way, Jingguo also put online a nice tutorial notebook for this project. If you are interested, I encourage you to check it out. So spin glasses, that's a model that physicists invented to describe disordered magnetic materials. The building blocks are those binary variables, plus minus one spins. And we can write down their energy function like this. So those are the couplings, and that's the local magnetic field. So the goal, one of the goals for spin glasses research is to find out the low energy configurations and the energies for them. This is a minimization problem. So such a formulation has the same, it's equivalent to Kobo quadratic unconstrained binary optimization problem. And it has broad applications for statistical physics, machine learning, and coding theory. However, finding ground state of such a problem on a general graph is NP hard. So it's a difficult problem. And actually, because of its NP hardness, Ising formulation is quite useful to represent many of the well-known NP complete problems. So physicists actually developed many of the interesting and useful methods and specialized hardwares around such an energy function in hope that they can also be useful in broader applications. To make this discussion concrete, we can think about Ising spin glass on a bucketball lattice or on a football. So by the way, this is actually a challenging problem we released to students in a summer school. So you might notice that because of the presence of these pentagons, then if you put antiferromagnetic Ising couplings on the lattice, there would be some frustration. So finding out the ground state energy and the configurations on such a bucketball lattice is not that trivial problem. So actually, we encourage the students to find as many solutions as they can find out in the challenge. And also because of the frustration, actually there will be some degeneracy in the ground state. You can imagine you flip some of these spins, the energy would be conserved. You still remain in the ground state manifold. So then asking the question about how many are those ground state is also an interesting question that's related to the so-called residual entropy problem. That's a counting problem. So the tropical tensor network that I'm going to introduce to you can be regarded as another way of solving this minimization and counting problems. So to start with, tropical algebra. So it's actually quite simple. So basically thinking about defining addition and multiplication between two numbers in an overloaded way. You replace the usual addition by minimization, and you replace usual multiplication by addition. That's it. So the elementary school student in a tropical world would be extremely happy because their addition table looks like quite simple. So their multiplication table. So essentially it becomes addition table for us. So by the way, you can think about adding infinite to x and the tropical algebra, it still gives you x, and multiply anything to infinite gives you infinite, and the tropical algebra. That is telling you that infinite plays a role as a zero element and the tropical algebra. So once we have this element, we can put those tropical numbers into a matrix or a tensor, and then we can connect those tensors into a tensor network. That's tropical tensor network. Then let's think about the contracting tensor network. The elementary operations we need to do are actually addition and multiplications. So in that sense, this overloaded tropical algebra is sufficient for us to think about contracting tensor networks. So by the way, now this is called a semiring because there is no inverse for the tropical addition. Remember, it's a minimization problem. Okay, so we can actually release a little bit about the mathematical requirement for us to think about contracting tensor networks from an ordinary ring to a semiring. So the claim is contracting a tropical tensor network would be a nice way to solve those optimization and counting problems for Ising spin glass. To understand that, actually to carry out such a calculation, the first step is to construct those local tropical tensors based on the Ising energy functions. The construction rule is actually quite simple. On each bound where you have this coupling, you just put a two-dimensional array with the coupling constant. And on each of the vertices, you put the local field to the diagonal elements of those vertices, and all the remaining elements you put 0. So essentially, if this is zero field tensor, you might recognize this is a copy tensor in the tropical sense. So once you have this tensor network, contracting them and the tropical algebra will give you the ground state energy. So to understand this, we can actually look at the usual algebra we had for contracting two tensors, or let's say multiplying two matrices. The elementary operation we need to do multiply those k indices and then sum them up. So and the tropical algebra, this becomes plus and min. So essentially, the physical meaning of each tensor in this tropical tensor network is that they store the so-called mean marginals. It's a tensor, or let's say a table, that stores the minimal energy configurations given all those external indices, let's say the spin index. And once you try to combine two pieces together, you need to look for those table elements and always marginalize, let's say, mean over those internal indices. So in that way, if you contract the whole tensor network, you get the ground state energy. So essentially, this is a reformulation of the so-called dynamical programming method in a tensor network contraction language. So it's not that new. So second of all, there is also a kind of physical way to understand why tropical algebra emerges in such a discussion. Because I guess in the tutorial and in many of those discussions before me, we already get this picture that for a general statistical mechanics problems, we can express the partition function as a tensor network, but that is at finite temperature. Then suppose we take infinite beta or zero temperature limit, then contracting that stat-mech partition function tensor network is going to give me the free energy at zero temperature, that is the energy. However, if you do that numerically with extremely large numbers in the tensor element, that is going to be numerical issue as discussed in those papers. So then a natural way to do that is actually to look at exponent, and by translating all those tensor network contraction algebra directly to the exponent, then very naturally you rediscover the tropical algebra that I was introducing to you. So that's for the ground state energy. But for many optimization problems, we also care about the ground state configurations. Okay, we care about all the solutions, and that's actually a nice way to obtain those solutions by taking gradient through the tensor network contraction. That was because if you view the computation process, a so-called computation graph, so in each individual step, you are doing differentiable operations. So it's actually possible to automatically compute this gradient. And because of the optimal energy, it's going to be a piecewise linear function of the local field. Also, in a physical term, the ground state configuration is going to be kind of a response to the local field fluctuations. So therefore, there's a way to directly get the solution by taking gradient. So here, I'd also like to mention an interclude. So the technique I just introduced to you is more like taking gradient through the whole tensor network program. Now people call that differentiable programming tensor networks. The idea was get strongly influenced by deep learning people, where they just train a neural network or a general computer program. So in many of the quantum physics and statistical physics computations, taking gradient through tensor networks is a nice way to help us to solve rational optimization problems, and also to help us to extract physical quantities like response functions and other functions, because very often you can write physical observable as gradient of some generating function that is expressed as a tensor network. So here, for computing ground state configuration, essentially I'm using the same technique, same idea. So for a third application, as I mentioned, the ground state manifold very often is going to be degenerate for frustrated systems. Sometimes I'd like to count number of solutions for the ground state. So here, there is also a nice way of solving that by generalizing those tropical tensor network elements. So now I'd like to think each of the tensor element as a tuple. The first element of the tuple is the tropical number that carries the energy information. The second one is the ordinary number that counts the number of solutions. So when I view this tuple, I just view them as kind of like the real and imaginary part of a complex number. So therefore, I'd like to work out the elementary multiplication and addition mathematics for those tuple. And once I work that out by contracting a tropical tensor network with this kind of generalized tuple as an element, for the first element, I'm going to get ground state energy. For the next element, I'm going to get the ground state degeneracy, essentially the entropy. So let me also draw connections to the existing work. There are also excellent works on counting solutions of constraint certification problems using tensor network contractions, and also to compute the residual entropies on infinite periodical lattices. So for this work, the first step, the starting point, is kind of different from what we did here. That was because for constraint certification problems, very often people just construct a tensor network with ordinary numbers, typically zeros and ones. Essentially, those local tensors encodes the kind of constraints that the ground state of those problems satisfy. So therefore, for some of the frustrated systems, sometimes it's going to be quite non-trivial to work out such constraints that was discussed in one of the very recent papers. So in our case, we care about counting the number of solution of a minimization problem, where the minimization problem is itself a non-trivial. So for example, on this football lattice, by contracting an tensor network with 60 vertices, you are going to actually find out, for example, this is one of the ground state configurations. So, and if you, let's say, flip some of them, you'll get a different one. In total, how many are they? There are actually 16,000. So that's quite a beautiful number to me. And so to wrap it up a little bit, so I talk about using tropical tensor networks to compute ground state energy, compute the ground state energy, ground state configurations, and to count the number of solutions in ground state. So conceptually, I have to admit that this is not conceptually new, because in the graphic model inference literature, there are actually identical techniques. So here, tensor network is just a reformulation of known technique. And the other thing is, even after this tensor network contraction, the problem is still hard, because we all know that exact contraction of a tensor network in general is a sharply hard problem. So this doesn't solve NP-hard optimization problems just by simply a reformulation. But what's the benefit? I would argue that the benefit is that after this tensor network reformulation, the computation framework nicely exploits the compute that deep learning community developed. That includes all those specialized hardware, GPU and TPUs, because they are really good at contracting tensors. The other thing is all those differentiable programming software. We can easily differentiate through this contraction process to get ground state configurations. So Jingguo also built a tropical glas to really accelerate the low-level operations of contracting tropical tensors. So here are some actual applications. As I argued, with those specialized hardware like Nvidia GPU, you can manage to quite easily get ground state energy and configurations on a square, cube, or this Chimera graph, or a three regular random graph. I think all those calculations can be done within a few minutes on a single GPU. And the application is also not limited to Ising spin glass. Just by working out the local tensors corresponding to their energy function, you can easily apply that to optimization and counting problems in a more general class of problems like post-model, max-2 set, and maximum independent set problems. So here, the non-trivial step, or let's say the interesting step, is always writing down the local tensors. Once you are done, it's the same framework, just contract those tropical tensor networks. And once you have this tensor network, the contraction becomes the really bottleneck. And in general, that's quite unfortunate. Contracting them is sharply hard, but even finding out an optimal contraction order is also NP hard problems. Therefore, people developed many of the heuristics for finding the order. So I recommend you to check out Johnny Gray's talk on Thursday. This is actually, I would say, the latest and quite a significant development along this line of finding heuristics of finding out contraction order. And finding out those contraction orders are relevant for inference in graphical models. And very recently, I guess it got a strong push from simulating quantum circuit. For example, here is a contraction tree that Alibaba Group developed for simulating this Sycamore circuit developed by Google. And the logic and the hope that we hold in this project is that once we translate optimization and counting problems for combinatorial optimization problem into a tensor network contraction, it makes sense for us to repurpose and reuse those high-performance tensor network contraction engines really for something useful and profit. And that's the idea. So in the remaining few minutes, let's say one of such an example. That is solving Ising spin glass with one of those quantum circuit simulators. So the initial intention for developing those simulators are really related to simulating quantum circuit. However, as we might heard, that quantum circuit and tensor networks that had a strong connection. So very often you can map one to the other. So now, how about we just map these tropical tensor networks into a quantum circuit? Then contracting the tensor network is transformed into a problem of simulating, let's say, computing the amplitude of such a quantum circuit. And for this, we can employ some of the quite generic quantum circuit simulator, for example, the one called YAO. So initially, it complains with a warning that the number you put into its quantum register is not complex, but it's this funny tropical float 64 number. But nevertheless, it's a generic code, so it still runs and spits out the answer. So this is, I would say, this is the Jingguo's idea, but I would say this is quite creative and crazy idea. Actually, it works. Using YAO, they can, let's say, simulate, for example, up to 62 square. That's 1,024 spins in about 100 seconds. And to get ground state configuration, you can use forward diff or reverse diff. That's two modes for computing the gradient through a computer program. There are some computing time and memory trade-off, but nevertheless, this is also quite efficient and reasonable. And an actual application to the D-Wave's Chimera graph, that's the graph they developed on actual hardware for quantum annealing. So for an 8 by 8 by 8, those class of problems with one GPU in less than 100 seconds, you can get ground state energy. And also for the first time, this code can be used to compute the ground state degeneracy on the D-Wave chip exactly. So you can really look at the distribution of ground state degeneracies for random instances for such a graph. And then you can compute the residual entropy on such a chip. So those numbers provide you a hint about the difficultness of those instances with such a quite special graph. So to wrap it up, so tropical tensor networks is a way to leveraging quite recent software and hardware development for combinatorial optimization problems and related counting problems. And to make use of that, we just need to have a generic code. And in the very low level, you just overload two operations, multiplication and addition. Then you are done. And up to this point, I talked all about exact contractions with exponential difficulty. So what would be the approximate contraction scheme under tropical algebra? So can we formulate, for example, variational methods or SVDs or power method under tropical algebra? So we can approximately contract an infinite, or let's say rather big enough tropical tensor networks. That's an open question. So with that, thank you for your attention. So in the very first slide, I put my email. In case you have questions, please email me. Thank you.